in this section, we're talking about angular and linear velocity and looking at their relationship with one another. First of all, we got to be reminded what linear velocity is, and linear velocity is an object moving with a constant velocity for a period of time. All right, and you guys know you've dealt with this your whole life. The equation for that is d equals velocity times time. The distance equals velocity times time. If you're traveling 60 miles per hour and you're going that rate for 2 hours, your distance you traveled was 120 miles. Easy enough, right? So when we're gonna start looking at angular velocity though, and that's gonna take a little bit of explanation. As an object moves along the circular path, the radius forms a central angle of theta. The change in the central angle with respect to time, theta over t, is the angular velocity of an object. So what we're talking about is we're talking about an object traveling in a circular spot. So let's just think of an object traveling around a center going like this. And best way to think about it is a tire. A tire spins and it travels all the way around in a circle, right? Around a central spot, the middle of the tire. Okay. So what we're talking about in angular velocity is how many times this thing goes around. Say this little guy, I don't know what it is, something, a point on a tire is traveling around a circle 5 times per second. All right, well, we want second with it. All right, 5 times per second. So what this thing's doing, so in 1 second, this thing is traveling around 1, 2, 3, 4, 5, all in 1 second. It's going that fast. All right. So when we talk about is angular velocity is telling us, well, how many times does theta change? Basically, how many times does this thing go in a circle? Does our angle in here change? Well, if this guy goes around in a circle, it completes a distance of 2 pi if we're just talking about a circle with a radius of 1, right? And then so its angular velocity would be, if it does this, if it goes around 2 pi and it does it 5 times, all right, it would have an angular velocity of 10 pi over 1 second. So it's traveling a distance of 10 pi for every 1 second that it goes. And that's what a regular velocity is. We're saying we're traveling 60 miles per 1 hour. So anytime we're talking about a rate or time, we're talking about distance all over time. Well, this is distance all over time. And notice we were dealing with radians because the radian is a fraction of the distance of a circumference around a circle. Well, this thing is going around that circle 5 times in 1 second, so it's traveling a distance. In this case, because it has a radius of 1, it's going 2 pi times how many revolutions it makes. Well, in this case, it's making 5 revolutions. So 2 times 5 is 10, and that's where we come up with 10 pi for our angular velocity. All right. Well, how do these two relate? Is if an object moves along a circle of a radius r, then its linear velocity is given by the equation r time velocity equals rate times time, right? And this is going to be our angular velocity. That's what we just talked about. So where theta over t represents the angular velocity. So if we're figuring out our linear velocity, how fast something is going this way, and if we know its angle velocity, if we take it times its radius, and so we take the angular velocity times the radius, we get its linear velocity, how fast it's going to travel in a linear speed, in a linear direction. Okay, so this will make more sense as we talk about this and we continue. Example 1 says a pulley of radius 13 centimeters turns at 7 revolutions per second. So what we have is we have a pulley here pulling something. It doesn't say a belt, all right? Okay, it's asking what is the linear velocity of the belt driving the pulley in meters per second. Okay, so we're looking for linear velocity. We said linear velocity equals r times our angular velocity. And our angular velocity is talking about the distance this thing travels per unit of time. So this thing has a radius of 12 centimeters, and it's making 7 revolutions per second. Okay, so we know its radius is 12. And if we're finding its angular velocity, it's traveling around, it's around a circle, which is 2 pi. And if it's doing this 7 times in 1 second, it's actually going a distance of 14 pi per 1 second. I keep putting a T on second. It should be a period. All right. So 12 times 14 pi over 1. This is this angular velocity. And the reason that we have to put this radius out in front is because, again, we can have different sizes of circles, much like the arc length problem. We can have different sizes of circles. So that's why this 12, all right? So in the example that I just made up at the top of my head, it had a radius of 1. So its angular velocity was just 1 times, 2 pi times 5 because it had 5 revolutions. All right? So that's what we're coming up. We're trying to figure out the distance that it's traveling, and in angular velocity, what you can think of is maybe I cut a hole in this circle and I just roll and I roll that circle out to see how much distance we're covering in 1 revolution. It's like cutting a bike tire and then rolling it flat out to see how far you've gone in a straight line. All right, so to find this linear velocity, then we just need to obviously multiply this. And so we're going to take 12 times 14 and we get 168, I think. So 168 pi all over 1 second, which is just 1. And if we actually wanted to figure out without a pi in there, we could type in 168 times pi. And we're traveling around 527.79 centimeters per second is our linear velocity then. Okay. So here's a good example. It says a truck driver drives 55 miles per hour. His truck tires have a diameter of 26 inches. What is the angular velocity in of the wheels in revolutions per second? Okay, so this truck driver, this is giving us his linear velocity. He's going 55 miles per hour. All right, so he's going 55 miles per hour. Now the thing we're going to have to do is realize what they give us and realize what kind of measurement they're using. Here we have miles and here we have inches. So we are going to have to convert our miles per hour into inches per second is what they actually want right here, which isn't, it seems tedious, but it's not too bad. So if we want to convert miles per 1 hour, we need to get things cancel out. All right, in order to get miles per hour to cancel out, let's go ahead and work on the miles part first. We just need to go back to, I remember teaching this in 8th grade math. So we just have to, for every 1 mile, there's 5,280 feet. And then for every foot, we want feet to cancel out. So the foot has to come in the bottom. For every feet, 1 foot, there's 12 inches. All right. So that's going to get our miles down to inches. So if you look at our labels here, miles cancel out here, and then all of a sudden we have feet, but feet are going to cancel out, and we're just left over with inches. Well, we want to get hours to cancel out. So for every 1 hour, there is 60 minutes. So now our hours cancel out. But we don't want minutes, we want seconds. So, and for every 1 minute, there is 60 seconds. Okay, so we cancel out the minutes. Nice to see that I spelled seconds right down here. Cancel, and we're left over now with inches per as a division seconds. All right, and if we go ahead and multiply these out, we'd have to take, we could look diagonal and cross out, or we could go 55 times 2,005 or 5,280. times 12. And on top we would have 3484800. So we have 3,484,800 on top, and on the bottom we'd have what, 3,600, because it would just be 60 times 60. So if we divide that, we get 968 inches per seconds. So I divided this by this and left over with inches per 1 second. So for every second, it's going 968 inches per second. All right, so we know it's linear velocity now. We know how fast it's traveling in a straight line. It's 968 inches per second. So we have 968 equals, and we want to figure out its revolutions per second. So we know its radius. If you remember our equation, our linear velocity equals the radius times theta over t, where theta was the number of revolutions times 2 pi. Okay, that's what theta equaled. Okay, so we know the radius. It gives us a diameter of 26 inches, so that means our radius has to be 13 inches. And we don't know what theta is. We don't know that. That's actually what we're looking for. We're looking for revolutions. All right, what's its angular velocity? And then we know per 1 second. So what we have here is we have 968 equals 13 theta. And then in order to get theta by itself, we're going to divide by 13. All right, and that doesn't go in evenly. However, we don't want to know, this doesn't really mean too much. What they were asking, they want to know how many revolutions per second. So how many times is this thing spinning? All right, so if we were to divide by 2 pi, that would give us how many revolutions per second. Because if you think what theta equals, if we change this, it'd be number of revolutions times 2 pi. So all of a sudden I have theta equals 968 over 13. But we want to solve for revolutions. So if we just say revolutions times 2 pi equals 968 over 13, because that's what theta is revolutions times 2 pi. We want to know what it is in revolutions per second. So to get revolutions by itself, we're going to divide by 2 pi. All right. And if we work that out, if we go 968 divided by 13, and then if we divide by 2 pi again, we get roughly 12 revolutions per second. So I hope that makes sense. And why we divided by 2 pi, because we were asked to find in revolutions per second. So we found his angular velocity, but now we want to find out how many revolutions that took. So what we do is we divide by 2 pi in order to get our revolutions, because theta, all right, theta, this symbol right here, is a number of revolutions times 2 pi. And we were looking for the number of revolutions. Okay. Moving on. Last thing to talk about is a sector. A sector is a region bounded by a central angle and an intercepted arc. I spelled that arc wrong. So if we have a circle right here, and if we have a central angle, all right, a sector is actually like a piece of a pie right in here. Okay, so here is the intercepted arc it's talking about. Here's the arc here. All right, and a sector is like a piece out of a pie. All right, to find the area of a sector, the area equals 1/2 r squared theta, where theta is the measure of the central angle expressed in radians, and r is the measure of the radius of the circle. All right, so we're going to do one example where we find the area of a sector. It says a sector has an arc length of 16 centimeters and a central angle measuring 0.95 radians. Find the radius of the circle and the area of the sector. Well, they give us some information here to let us know. It actually gives us an arc length, and we got to think about what arc length equals. We're going to have to think back to last section where we said S equals R theta. All right. So we know the arc length is 16. We do not know what the radius is. That's actually what we're looking for, but we also know where what the central angle is, and that's theta. That's 0.95. So in order to solve for our radius, we're going to divide by 0.95. Okay, so 16 divided by 0.95, and I get our radius is roughly 16.84, all right, centimeters. Now that's a radius. So now that we know our radius, we can go ahead and find our area. So it's going to be area equals 1/2 times the radius, 16.84 squared times times the radian measure. All right, so our central angle, 0.95. And after I type that into my calculator, I get around 134.7 square centimeters. So that was an area of a circle, or area of a sector, which is basically a piece of pie. So this inside here. So just a part of a circle. Well, I hope this helps, and we'll see you in class.